in chapter 24. That's going to be on carboxylic acids and esters. And the nice thing about these chapters is hopefully you're starting to pick up on the patterns and trends for naming, so that when we look at how to name carboxylic acids and esters, it'll go pretty quick. The other thing that you should be picking up on that we'll cover today is the functional groups, and them are ones you've seen before because you've made both of these molecules in the alcohol chapter. And also when we start talking about boiling points and melting points, that stuff is all the same too. It's just a new functional group that you have to kind of think about, you know, what intermolecular forces are available to it or how it can interact with each other. But nothing new is there as far as we're not introducing a new intermolecular force or anything like that. So the functional group for carboxylic acids is a carbonyl carbon, so a carbon double bonded to an oxygen that also has an OH group attached to it. And then the other thing that's attached to that carbon is just an R. And what does the R stand for? Yeah, it's just the rest of the molecule, right? It's mostly just alkane parts. I mean, we don't consider other functional groups there and things like that. So it's basically just saying everything that's not that functional group. If you see it, sometimes you'll also see it written like this, where instead of explicitly showing that double bond, they just write it all out kind of like a condensed structure. And sometimes if they're exceptionally lazy, they'll actually do something like this, where they lump the two oxygens together, even though one is single bonded and one is double bonded. But if you try to draw that Lewis structure, you pretty much notice that you only have one option available to you there. And then to compare that, esters are very like carboxylic acids, but instead of having an OH group there, that H becomes another R group to it. And so sometimes you'll see them written like this, RCOO R prime. And the prime there simply means that the two R groups don't have to be the same. They can be different on either side of that molecule. So those are our two basic functional groups. Now if we want to talk about naming them, for carboxylic acids, we just changed the E to oic space acid. So notice I'm putting an underline in there because I want to basically highlight the space. Meaning when you type them in the computer can tell where you want your spaces pretty easy. When you guys type them up on a piece of paper, just make sure you leave that space in there for that oic acid. And then because it's always on the end, kind of like an aldehyde, then there's no numbers. Because it's always number one and it's always at the end. And so if we look at just a simple one with 4 say carbons and an OH, that would normally be butane, but we're going to call this butanoic acid. And so we have that oic acid ending. And it's kind of like carboxylic acid. So I mean the name and the how you name it are fairly similar to each other. And if we add any side groups on it, you know, we always number from our carboxylic acid end, 2, 3, 4, 5. So even if I started from where I labeled the number 5 carbon, the methyls would have lower numbers. Remember that our functional group always has to have the lowest set of numbers. So we'd say that this is 3,4 dimethyl pentanoic acid. Oops, make that nicer looking. I think carboxylic acids, kind of like aldehydes to a certain extent, are probably one of the easiest molecules to name, simply because you don't need a number and you always know where to put the number 1, right? So what are some things I could do to screw us up? Make it harder.
Wait, you said it was in a location number. Why is that on number 1?
That's the L from methyl. Sorry, that's... That's Jay's sloppy handwriting. So how can I make it harder? Sure, we could have two of them, one on either end of the molecule. What do you think we'd call that? So it's, butane, right? So it's butane dioic acid. So the di is telling me that I have two carboxylic acid functional groups on it. So just like if we have a aldehyde with two functional groups, we call it a dial. If we have an alcohol with two functional groups, we call it a diol, meaning that di, if there's more than one of that functional group in there, always gets stuck right before the functional group ending. Yes?
So is there a space between butane and diol, or is that
No, that's just my crappy handwriting. So I should point out, and maybe I'll just start doing it, that way it's obvious. I usually just start writing things like that so that when there's a space, you know there's a space. And you can't do that on the computer because the computer can actually know what a space is. But if on a test or anything else you want to show me that you explicitly know where the spaces are, go ahead and put them in there. So far, where's the only molecule that has a space in it? This one. Now, of course, just to keep on that trend, esters will have a space in them too. We'll talk about why that is in a minute. But if you want to explicitly show the spaces when you're writing them down, go ahead and stick an underline in there. What's another way I can make it harder? Well, what other type of functional groups can I mix in with it? Yeah, what if I had something like this? Now the nice thing is the numbering's pretty easy because we have to start from the carboxylic acid carbon. That's that carbon right there. And then how do we express a double bond? Yeah, so we're going to call this 4-hexene oic space acid. So just that little E, that's the only thing that's telling you that there's a carbon-carbon double bond in it. I would say on the homework problems for the last two chapters that I slipped in one of those in each homework. And if you're going through it pretty quick, what is this? Oh, I like this. Windows is automatically going to restart my computer in 14 minutes without me even getting a... If this wasn't taping, you would hear a string of explicitives like 5 minutes long. It would be educational. I've been working on my swearing. No, just kidding. So anyway, you got to pay really close attention. The other clue that there's something else funky going on is if there's a 4 in there, you should know that, well, obviously there is something in there that has to be numbered, right? And since we don't number the carboxylic acid functional group, that number must be telling me about the double bond, right? Or something, meaning look for something in that name that needs a number. What if I do something like this? So this would be 4-pentanone, right? Pentan dash actually pentanone. That one's kind of weird. I'll be honest, I don't put any of those on there. I don't even have any of them named. 4-pentanenoic acid. No, I don't generally. You know, there's like, it's okay to mix in a double bond here and there, maybe an OH group because those are easy, but after a while I just stop torturing you so we don't get so creative. One other one that we should remember should be review. What's that? Bitch acid, yep. No. Benzoic acid. And so, you know, you might see one in there with an ortho, meta, para, or something tossed in. It's good review for chapter 20. It's good review for when you have to take the final exam on this. So we try to mix in those and keep you honest. Okay, let's take a look at esters next. Do you guys remember when we first talked about an ester?
Some reaction.
Yeah, some reaction made one. Excellent. So the reaction that made one was we took a primary alcohol plus some carboxylic acid. You guys remember what type of reaction it was? Yep, dehydration. And so what we did is we said we can take an H and an OH, and then, you know, I need to connect that part to that part. And so this 4-carbon fragment, that came from my carboxylic acid part, whereas that 2-carbon fragment came from my primary alcohol, right? And of course I get plus H2O if it's a dehydration. And so the way we think about esters is there's two parts to the ester. There's always the part that's coming from the carboxylic acid, and there's the part that's coming from the primary alcohol. So we consider this part our main chain, and this part is a side chain. But it's strange because you have to think about it. I can also have side chains on the carboxylic acid part, right? And I can also have side chains on my alcohol part. And so in order to differentiate it, the way we really name this molecule is we're going to call this ethyl space butan O8. Pointing to the primary alcohol part? Well, that's the part that came from the alcohol, right?
What is that side chain?
Right, so that's what we're saying is the ethyl. So notice that we separate the alcohol, or that's that R prime side chain with a space. And of course, the ending we get is we take E and we go to O8. So here's that other one with a space in it. Hmm?
It always has ethyl.
No, because it doesn't always have to be an ethyl. We'll show you a bunch of examples. I feel like I'm on a countdown here. I know my computer's just going to go beep in like 10 minutes. That's okay. Oh yeah, and Jasmine, we're sorry, computer totally blue screened on Friday, so no lecture. So if I make it harder, meaning I make things bigger, so if I'm trying to name this molecule, notice that this part here we consider a butyl, because it's 4 carbons, and then there's a space, right? And on this side, we have, if I were to just name that kind of, we have a 4-methyl, and then it's 5, so it's pentan O8. And so if I stick the parts together, I've got to keep that space in there. Butyl 4-methyl pentan O8. And so this is telling me what's on that R prime chain. This is telling me sort of what's on that R chain, if you're kind of thinking about them like this. So is everyone with me so far on these? The real trick is just to realize that there's kind of, I mean, that we have that, the part before the space is describing whatever's sort of on the side with just the single oxygen. What about if I do this? let's see, 1, 2, 3, 4, 5, 6, 7 carbons there. And there's 2 carbons there. Which is the longest chain, 7 or 2 carbons? This is considered the functional group. So it's the side with the carbon double bonded to it. And so we actually really call this heptyl space ethanoate. And so our longest chain is always on the side that came from the carboxylic acid, meaning the side that has the carbon double bonded to the oxygen. And also, while we're on it, notice that I can draw all of these at least 2 ways, right? Do you guys recognize that this is the same molecule? It's just which way I drew. So you have to be careful when you're naming these. Sometimes the alcohol part's on the right-hand side of the molecule, right? Sometimes it's on the left hand. And I have to admit, if I'm drawing them just to draw reactions and everything else, I'm pretty good about, well, I usually just am consistent and always draw the carboxylic acid part first. But be aware that they can be mixed up in any sort of way, right? And then you can also get some kind of weird things going on. Because, like I said, and don't worry about this too much, you won't have to name too many of them. We'll do that. So I can actually have side chains on the alcohol part too. And so if we were to name just the alcohol part, kind of, we would say that that's 2,3 dimethyl, right? And then that would normally be butane, right? But since this is going to be a side chain, that becomes butyl, and then we have our space. So it looks like we kind of have a side chain on a side chain, meaning I've got YL endings attached to something that has a YL. And then on this side, it's just 1, 2, 3, 4, 4 dimethyl pentanoate. And so when I put them together, I get a huge name, actually. Dimethyl butyl space 4,4 dimethyl pentanoate. And so it's almost like esters have split personalities, meaning we treat them completely separate from each other, meaning the alcohol part has the alcohol part on it. Oh, it's just going to keep saying it's 15 minutes away, and I can just keep clicking restart later. That's pretty nice. Annoying, but nice. Boy, and I thought my ex-wife was a nag. So 2,3 dimethyl butyl 4,4 dimethyl pentanoate. Okay, so let's take a look at the intermolecular forces available. So here's my carboxylic acid. Oh, I'm sorry, I forgot one last thing we had to cover. We'll just skip a slide. Sorry, I just glanced down at my paper and noticed that I need to do this. We've seen these a couple times, right? What did we call this? Yeah, it's called a carboxylic acid salt, but it's named like an ester because it really is more of an ester than a carboxylic acid salt. Meaning we would name this sodium space butanoate. Because what the sodium is doing is it's taking the place of that R prime group. And so we would just name it as sodium. Or if we have something with a, what was the other type of salt we always had? NH4 plus. Do you guys remember what that is from first semester? Yep, so this is just ammonium butanoate. So sorry, that was that miscellaneous topic I need to throw in, which is how to name a carboxylic acid salt like it's an ester, which is a little strange, but that's okay. And it makes sense if you ask me. I mean, to name it like an ester, I don't know if it makes sense to call it an ester salt or a carboxylic acid salt. The reasoning it's called a carboxylic acid salt is that in general, if we do form one of those in a reaction, or you do have one of those that's floating around in your body as a biomolecule, you know, sometimes it'll have the sodium attached, sometimes it'll have the hydrogen, but it'll never have some weird R group attached. So it's always going to be a carboxylic acid sort of derivative. And it behaves much more like a carboxylic acid than it behaves like an ester. Okay, so back to intermolecular forces. So what intermolecular forces are in my carboxylic acid? Heck, maybe we should even draw it bigger so we can illustrate it. Yeah, certainly we can form hydrogen bonds. But what else is there? Louder. LDFs are always there. That's the R group part. Now, when does that even matter, though, in general? Only when we're talking about solubility, right? Or if the functional groups are the same, but the size is different. So what's the other one that we have here? Yeah, this has a partial negative and a partial positive. So this part of the molecule can actually form a dipole-dipole. And so notice that this is the first molecule that we've had that has all three of these functional groups, or all three of these intermolecular forces kind of associated with it. And so where do you think that this is going to fall in our grand scheme of things? So let's take a look at, say, boiling point. Where do we think it falls in our boiling point scheme? Yeah, so remember we had our alkanes, enes, and ines down here. We said that just slightly above them is esters, right? And slightly above that is aldehydes and ketones. And a good chunk above that is our alcohol groups. And then above that is our carboxylic acid. We really should expect our carboxylic acids to have fairly significant boiling points. Where's my little chart? I have a little chart with some numbers on it that I usually pull out just to kind of give people a relative idea. It's actually printed in the study guide for this chapter too, so if I can't find it, you guys have it available to you. I just was gonna put some numbers down, but if I can't find it, then that's okay. Boy, you would think since I put everything in one folder, and I found it this morning. Oh, here we go. So I don't remember which one I gave you guys. There's a couple of them here. But for instance, if we compare something that has about 3 carbons, then you know, we're down here for alkanes at, oops, let me look the number up, minus 42 degrees Celsius for its boiling point. Meaning, what do we know about most propane, for instance, because that's 3 carbons, right? Here, let's redraw that. Well, we can fit it in there. So, see, this is propane, right? So we know that that's a gas at room temperature. And then if you're kind of coming up here, this should be ether. Let's see, for aldehydes, we're talking at 49 degrees Celsius for just propanal. And then for our alcohol, we've got that all the way up at 117 degrees Celsius. So that's just talking about propanol. And then if we talk about our carboxylic acid that has 3 carbons on it, then we're talking, this one isn't that much higher, but 118 degrees Celsius. So it's not that much higher in this example, but in general it's significantly higher. Well, one of the things that we can do is realize that if I draw these sort of sort of geometrically, sort of not because my drawing skills suck, these molecules line up really nicely like this, to where that hydrogen bond can form an interaction with the dipole on that one, and this can form a hydrogen bond with the dipole on that one. And so we get these molecules that are called dimers, meaning there's basically two molecules stuck together. And so there's twice as many, or there's more interactions therefore harder to pull apart, which is what we mean when we say oil, right? I'm simply saying that these numbers are closer than I would expect, but it's a very small molecule, meaning as the molecules get bigger, you'll find that that distance is larger. I'm trying to find where my other one is. I have two sets of data. One of them uses that little 3 molecules, and then I think the other one used molecules that are like 5 carbons long, and so that was a little bit more obvious, the difference, but I don't know. Apparently, oh, here it is. Never mind, it's the exact same one. I just have 2 copies of it in there. So I'll go look for that and see if I can pull it out. But in general, carboxylic acids are going to have higher boiling points than your corresponding alcohols by at least a small margin. But notice the big jumps in here are things like simply going from an aldehyde or a ketone all the way up to an alcohol. What do we expect for the solubility of carboxylic acids? I never leave myself much space, so we're going to be smart. What do we think about the solubility of these? So we should expect them to be very soluble, kind of like alcohols, because not only can I form a hydrogen bond with water, but I can also have that dipole-dipole interaction with the water molecule. And so there's lots of interactions that can occur. The molecule looks a lot like water. Lots of partials in there. And heck, we can even have one there for the heck of it. So there's restart later. So there's lots of interaction between the functional groups. And you can go through and you can label those specifically. And so what that means is that for less than 4 carbons, it's basically infinitely soluble. For 4 carbons to 8 carbons, it's slightly soluble. And then, of course, we know that as molecules get bigger, then it becomes insoluble. So here, you know, if we're taking a look at that molecule, 1, 2, 3, 4, 5, 6, 7, 8, this little part right here is soluble, but this alkane part is insoluble. And so generally we have kind of a war going on, right? The bigger the molecule gets, the more the alkane group takes charge. Excuse me. The more the alkane part takes charge, and the less and less soluble it becomes, or the more and more like an alkane it behaves. But we'll learn, for instance, in chapter, when we study lipid bilayers, that these molecules actually have not quite, well, they form layers where one side of the layer is hydrophilic, meaning it loves water, and one side of the layer is hydrophobic. I should also point out that all of these things we've been talking about, and I've said it before, come back later on, meaning when we go through the biochemistry chapters, when I say, you remember from organic chemistry part this, Well, you've already learned half the chapter then each time. If you're having to learn it all over again and learn the biochemistry stuff, then it's a lot more work. So like I said, work hard now, slack off later. Or, you know, sometimes it's work hard now, work hard later, and still work more. Okay, so that's carboxylic acids. Let me go back. We got one last functional group to talk about, and then we'll think about reviewing some reactions or whatever people kind of want to come up with for questions. I know, talked to a couple people last night. It seems like things are going okay-ish. I don't know. Oh, you're gonna get picky on that here. No, that's less than 4 carbons, between 4 and 8. Don't worry about too much. I'm not going to ask you a question where it's 3 or 4 carbons and you're going to have to do it, right? I always ask simply which is more soluble. Although, you know, it's a good thing to say I could simply ask you a question whether, you know, something is infinitely soluble or not. But I tend to not ask questions like that because that's rote memorization to a certain extent. Oops. Okay, what about esters? What intermolecular forces are present in an ester? Actually, let's do it like that. Yeah, this has just got a dipole-dipole. And if we're being, you know, keeping track, we can also have LDFs on the R groups, of course. So esters have very weak intermolecular forces. And so they're on the order of sort of, well, actually, let's just go ahead and do it. So we've got alkanes, oops, ANE, ENE, YNEs. Then we have ethers. Then we have esters. And I would say that these are almost the same. So esters aren't much more. And then, of course, we have aldehydes and ketones, alcohols, and I ran out of room for the carboxylic acids up at the top. So if you look at it, you know, these are just LDFs. Ethers have a very weak dipole-dipole. In fact, all of these parts in here have kind of weak dipole-dipoles, and then we get to some hydrogen bonds for them. And so esters behave much like ethers and or much like aldehydes and ketones because all they have is that little carbonyl group. Alcohol and then carboxylic acid. So alcohol and then carboxylic acid is higher than that. So these are fairly nonpolar. Therefore, they're fairly or mostly insoluble. In water. And in the random factoid category, since there's not much of interest for the intermolecular forces or anything like that, if they have less than 10 carbons, they tend to be a little on the stinky side. But if they have greater than 10 carbons, they're basically fruity. And that even is, wait, do I have that? Yeah, greater than. So like for instance, if we take a look at this is still small, but this smells like pineapple. At least that's what they tell me. Or if I have a very similar one where it's just got a methyl group, that's supposed to be what rum smells like because it's got some of that in it. And there's an entire book in your, or table 24.3 that is at least interesting, meaning you should be reading your book and you should be kind of thinking about things like that. And then if we get really big esters, meaning, and I'm not going to draw it out because I don't feel like counting it, but if this is on the order of 20 plus, and oops, that's supposed to be an R prime, that's on the order of 20 plus, we call those compounds actually waxes. So all wax is a gigantic ester. What do you know about waxes? What's one of the big properties that we use them for? What? I just couldn't hear you. You got to talk louder. How many people go out and wax their cars or wax their furniture or polish their furniture? Basically, car wax is just a gigantic wax. Or you can wax other things too, but that's more painful. And actually, I don't know what they use, if that really is wax or not. I guess probably they originally used wax for that. I don't know.
You ever say a word too much and it makes sense?
Wax?
That's what is happening to me.
It is possible. There are words that sometimes when I spell them, I'm like, that's not really a word, is it? Or something just looks wrong even though it's right. Okay, so let's review some. What type of questions do people have going into the test? Have you sat down and organized all the types of reactions in your head? Have you started playing with having chapter 22 and chapter 23 mixed together? I printed up a bunch of more practices. It seems like the randomization on it is broken a little bit. For some reason, it seems to be putting a lot of combustion reactions. Probably won't be more than one on the test. Have you guys come up with a order that you're going to do things in? Just like in math, you have PEMDAS, parentheses, exponents, multiplication, division, addition, and subtraction. Same thing with reactions here. If you have an approach to them, if you have a way that you're going to say, I'm going to get rid of, or I'm going to do this type first because it's easy. Or sometimes I like the opposite. I'm going to do this one first because it sucks ass, meaning it's the hardest one. And so whether you want to do the easy ones first because they're easy, or do the hard ones first to get them out of the way and then just relax on the easy ones, you can. If you think they're all hard, then you need to study more. So what type of approaches have people gotten or thought about? Have you characterized or categorized everything yet?
The only thing I really do is just whatever I feel like I'm going to struggle the most on, I try to do it first.
Yeah, I like to do the hard ones first. What would you say the hardest reaction is from this section?
I don't like the one that has diluted. That's just,
Okay, so she says she doesn't like aldol reactions. Aldol reactions can have multiple products, therefore they suck. And they're kind of hard to draw. So let's take a look at how we can recognize the types of products and how we can make it easier to draw. So actually, let's make this a ketone. So what we should do is say I've got A and B, right? And then, for instance, on A, there's only one spot that that molecule breaks apart at, right? Does that make sense? Do you guys remember the alpha hydrogen? And then in B, how many spots do I have that can break apart? 2. So really, if you want to say it, I can have B1 or B2, right? Meaning there's more than one spot. So when you have this, you can always make A and A. And for B, you can actually make more than one B, right? Meaning if I add B to itself, I can have B added to, or a B1 added to B, or I can have, say, a B2 added to B, right? So the idea is that what you have to be good at is picturing all the various combinations that can happen. And to a certain extent, it's kind of like when we did the substitution reactions and we had to label all the hydrogens and then you had to circle the favored product. You guys remember that from chapter 19? You have to have kind of a good visualization. And so what you're kind of saying is that if I'm taking A and I'm adding it to A, well, there's only one hydrogen that reacts, right? If I'm adding B to B, well, I could either add the B1 hydrogen or the B2, right? But the part that it gets added to, that carbonyl group, is the same for both, right? And then, of course, I can have A added to B, right? Which is kind of how it's drawn. And then I can have B1 adding to A and B2 adding to A. So I can really have 6 combinations. That being said, what's the one thing that Jay kind of mentioned that on the test he's going to go easy on? So are you really going to have one that you have to have 6 products for? No. But if you can master the one with 6 products, can you get all the other ones? Yeah, so it's good to stretch yourself and try to do it. Realize that you'll probably have one that ends up with either 1 or maybe 1 or 2 or 3 products tops. And then how we think about doing the reaction is sort of up to you guys. I am going to redraw it because I want to get rid of some of the extraneous stuff. So if I'm adding, well, actually, let's start off easy. Let's do the A to A, right? And so what I'm saying is that's the same reaction. It's just now I'm thinking about it in terms of just 2A molecules. And I'm consistent in that I like to go like this. Here's my hydrogen that's breaking, right? And where am I adding that on the other molecule? That hydrogen goes to the oxygen, right? And so that means that the carbon here has to go to the backside of that molecule and react with the carbon there. So notice the parts, when they're broken together, have to connect back across that carbonyl group double bond, right? And then I know the part that some people struggle with, and this one isn't too bad, I think, because it's just 3 carbons, but how do I connect everything together? Well, I say be really systematic about it. Always draw your molecule that you're adding to, and you know it's always going to get an OH, right? And then what you have to do is you have to mentally go, okay, that's that carbon there, right? That has to be connected to this carbon here. So just draw a bond to a carbon. And then just ask yourself, what's attached to the middle carbon in A? I've got a methyl group, right? And I've got a aldehyde group. Meaning I physically look at, gosh, I don't think I can point to that. Oh well. I physically look at this dot right here and say, what's attached to it? Well, I've got a methyl group, right? And the aldehyde group. That's finding wonderful to jump up and down like that until you knock loose all that snot. Now you're drowning. And then the other tough part is the computer likes to redraw these and go, well, this is probably the longest chain, right? So the computer will, of course, draw this 5 carbons in a row and say, well, there's an aldehyde on one end, there's a methyl group there, there's an OH group there. So the computer will draw it like that, and you'll be like, well, shit, that's not what my picture looks like. But you guys should be able to number your picture and number the one on the computer and kind of compare them and say, okay, is that the same or not? Right, so, but here's the 6th one because it's a side chain, so I didn't number it. But I mean, there is 6 carbons. You're right, if I'm taking 3 carbons plus 3 carbons, I better get 6 carbons. And then the other thing to look at is say, is this beta hydroxy? Meaning, here's my alpha, here's my beta. So alpha hydrogens react to make beta hydroxy ketones or aldehydes, right? So you can double check that yourself too. So that's our AA, right? And we said that we can do AB. So here's A, here's B. And again, since I'm saying it's AB, I'm still breaking apart the A molecule in the same way, right? That hydrogen still has to go to one side, and that carbon has to go to the other side. So when I'm drawing the product, I again draw my molecule with an OH group, and then I simply have to connect the dots. So that dot has to be connected to the other carbon, and then that other carbon has a methyl and a aldehyde group, right? And I can do my checks. Here's my alpha, beta hydroxy. And then if we really wanted to, we'd say that that's 1, 2, 3, 4, 5, 6. So of course the computer is going to draw it like this. 1, 2, 3, 4, 5, 6. And then it's going to have a methyl group, and this is going to have a methyl group and an OH group on it, meaning the computer will draw it differently. So that's A being added into B, right? So those are probably the two easier ones. I got to be honest, when it starts getting into the B's and the A's, that's a little harder, right? So remember, we also said we can have B1 and A. So notice I'm flipping the order I draw them in, because now what's being broken apart is the alpha hydrogen on the B1, and I forgot which one I labeled B1, so I have to go back. I labeled B1 as being this one, right? So again, break that bond, add the hydrogen to one side, realize that this carbon has got to be connected to this carbon, right? And so again, draw the A molecule, draw your OH group, and then connect those two carbons together like that. And this is just a thought process that, I don't know, that's the way I can know that I'm going to make them properly. And you have to come up with your own thought process. I don't know if my thought process is the best or not. Seems to work, usually. And so what's attached to this carbon on the B1? I made that kind of excessively long, sorry. There, that's a little less excessive. What's attached to this right here? An ethyl group, right? So just draw an ethyl group on it. And then it's also got another ethyl group, and then it's got a ketone on this one. Kind of looks like somebody running almost. I don't know. I always think that these look like pictures. And so, you know, here's that new bond, right? That used to be your carbon-carbon double bond. Notice that this is alpha. It's again a beta hydroxy something, right? And if we want, I'm going to draw the other one on this, except I'm going to use red. So this would be my B2 one, right? So if I draw it like that, then what I do is I still draw this part exactly the same. It's just that now the parts that need to be connected together are the parts in red. So what's attached to that red carbon? Well, it goes 1, 2, 3, 4 more carbons. So 1, 2, 3, 4. 1, 2, 3, 4, 5 total. And on the one next to that, it's got to have a double bond. And so it just looks like that. So, are you guys picking up on the pattern? By highlighting what parts you're connecting together, I kind of think about it like I'm connecting Legos together, or really I remember Tinker Toys when I was a kid, but I don't think any of you guys remember Tinker Toys too much. Did anyone have Tinker Toys when they were kids? That's the ones they have like circles that have little holes in them, and then rods that you can stick in them. And if I had Tinker Toys, I'd bring them to school, but I don't have any. Do you guys remember Lincoln logs?
Yeah.
You could build a log cabin. What? Yeah, that's the problem is people started saying like just buying Legos instead of all the different varieties. Probably because Legos are, in the end, a little bit better. Although now they've got so many little specialized parts, it makes me want to scream. And how much Legos cost these days? Holy crap, for like 0.2 cents worth of plastic. Ooh. I know they have to ship it and stuff like that, but really. So there's a bunch of them. What's the one we haven't done yet? Yeah, we need to do B1 being added to a B. And so we've really got two of the same molecule. It's just that we are realizing that we're breaking apart one here, and again, we're adding the hydrogen to this side, and that carbon needs to be stuck on that side. And so again, draw the second molecule first. And you don't have to do that. If you want to draw the first molecule first, you can. I don't know. It's just, this is the way I do it. And then realize that that carbon here has to be connected to that blue carbon. Draw the bond extra big if you need to get it away from the rest of the molecule so it's not too crowded. And then just ask yourself, what's attached to that carbon in the B1 molecule? An ethyl group, right? And two more carbons with a ketone on it. Kind of looks like a running man with one really long arm and something on his knee. Jasmine. They're the alpha hydrogens, so the ones that are right next to the carbonyl group are weaker than the other ones, and so you can do this addition reaction. And then of course the last one we can have is B2 plus B, but I think you guys are starting to get the idea, I hope. And so practice makes perfect, so if I'm doing this hydrogen right here, that goes to this, and it's this carbon and this carbon that get the new bond, right? Because we're really just adding across that double bond. So do my OH, do this down to here, and then it's got to have 1, 2, 3, 4, 1, 2, 3, 4, and on the one right next to it, it has that. So there's my two carbons. So if you've got too much going on, simplify it. Put a big dot on the parts you want to connect together, or show where you're actually breaking the molecule apart. Jess, you with us? Making sure. That head's nodding pretty hard. Okay, so that's aldol reactions in a nutshell. How are you going to recognize them? Yeah, there's two ways you can do it. Dilute NaOH. The other way I recommend it is, you can also remember that it's two aldehydes, two ketones, or an aldehyde plus a ketone, meaning that's another way to recognize it. I'm to the point, though, where what I'm starting to look at is, if I've got carbons double bonded to oxygens, what's the only thing that I can do? Well, I do have some other choices. Like, for instance, if you saw a single molecule like this, meaning we're even trying to be tricky, you certainly could see this, right? And we've certainly learned this, either reduction or, what is it, H2 and nickel. I don't remember which way I'm in doing it. We certainly can do that, right? I can certainly even put it, plus NaOH plus Cu, 2Cu plus ions, right? Meaning there's a lot of things I can actually do to an aldehyde. But if I eliminate all of those choices first, what am I left with? And I got to be honest, pretty easy to recognize. I'm not saying it's easy to do, but if you haven't gotten the idea that O means oxidation yet, go home. Just, go home. Now, this one's new, but again, that's memorization of some sort, right? And this you should recognize is also the oxidation one. Meaning, if you can eliminate a bunch of things, then there's only one or two options left, right? And the more you think about these reactions on a big scale, meaning not getting stuck in the individual steps, but in how I'm going to recognize, how I'm going to organize, what's going to trigger the event for me, the better you get. Now, some people, that's good enough. They'll just remember that. And then if they can remember what to do, if they also associate that word with, say, alpha hydrogen and addition, then you should be able to kind of figure out what's going on, right? Meaning, if you have all the words associated together and you know what all those words mean, if you understand the definition of alpha hydrogen, if you understand what we mean by an addition reaction, then you don't have to remember any specific details, right? You can reconstruct it from the parts. Or, you know, if you want to remember this part, you can. Whatever it takes to trigger it for you, go ahead and do that. But you've got to have a little bit of a trigger or something that, you know, says, hey, there's some in my office, in my book bag. It's sitting on my desk probably. So that's good. So good question. I would say of the reactions, that's by far the hardest to physically think about usually and draw. Again, don't focus too much on it. Well, I hate to say don't focus on anything, but you know, if that one gives you fits and you never feel like you're going to master it, then save yourself a lot of stress, lose the 2 points on the test from that one question, and move on with your life.
I like that helpful. I don't know why it didn't make sense on Friday, but even that helped. I mean,
My personal choice is, or personal choice, I have no choice. My personal opinion on it is to learn something you have to look at it, try it, go back and look at it again. And so until you've done the try phase, it's meaningless. Like for instance, if you haven't even started your homework, this was probably almost incomprehensible or it won't help you. Meaning you've got to try stuff. You've got to kind of fail at it maybe even a little, or at least not feel comfortable in your success. And then the second time around, I find everything is much easier in life. It's why I have these review sessions. It's why I assign homework. I can't imagine anyone sitting in lecture, nodding their head and going, oh yeah, I can go do that on the homework. Wow. I mean, really, that'd be awful tough. How many people here can just, like when they do the homework, they don't even bother looking in their notes. They've just got it all in their brain right away. Yeah, no Einsteins in this class. That's okay. How many Einsteins are there in the world? You're related to an Einstein?
yeah, my grandpa. He's smart as hell. Me and the
Me and who?
Einstein himself.
Yeah, what I'm trying to say is that everyone has their different learning styles and whether it's going to be easy or not. I don't think very many people can just look at this and do it. If you're not trying it and doing it as an iterative process, then you're going to struggle when it comes time to the test. If you try to do that iterative process the night before the test, can you imagine how well that's going to work? No, you got to study this stuff well in advance to get it. Next question. I'll keep answering questions, or if you guys don't have any, you can leave.
Homework.
Sure.
It asks about what test you would use
Yeah?
and how would you differentiate between, they're both primary alcohols, but they have phenol groups on ethanol.
Well, there's your first mistake. So here's the molecules, right?
Yes.
They're not both primary alcohols, are they? This is a primary. This is actually a secondary. One of the things that question is supposed to be making you link up is things that you've studied before. So what are possible tests that you can use to distinguish between things? Meaning, if this were a multiple choice question, what would the answers be? That's what I'm saying. No, give them to me. Yeah, so Lucas, right? And that differentiates primary and secondary from... Actually, that one differentiates them all, right? What other tests have we learned? Yeah? That was called toluenes, right? What does that allow you to differentiate? Right? What else have we learned? Meaning, if I were to write this as a multiple choice question, these would be the multiple choice answers, right? Chromic acid. What does that allow you to differentiate? Right? And it should allow you to differentiate between aldehydes and ketones, even though we didn't use it for that, because we know we can oxidize aldehydes. Can we oxidize ketones? No. What other multiple choice answers do I have for this? You could use solubility for some types of molecules. In this case, do you think that these would be very different solubility-wise? But I'm gonna put solubility down, because if I gave you an alcohol and an ester to separate, then you could separate that based on solubility if the alcohol is small and the ester is large, right? So that's a good one. What else? Yeah, phalings. That's the copper 2+ ions going to Cu2O, which is that brick red precipitate. And that, of course, differentiates between aldehydes and ketones. So, you know, if I really did make a multiple choice test, instead of write me a sentence or say something about these, then, you know, these would be the multiple choice answers. So if you have a list of all the answers, it's a lot easier to think about the question, isn't it? Does that make sense? Meaning, if you really understand each of these tests and what they test for, then when you go and look at those molecules, you should look at it and go, well, do I have a test that tests for phenyl groups? No phenyl group test, right? So it's obviously the phenyl group's just there to throw you off the scent. So then you have to say, well, they're both alcohols. Well, what have we learned about alcohols? We've got several tests that differentiate between them, right? So then you should start thinking, well, maybe one's primary, secondary, or tertiary. Meaning, if you can list all the tests, you know what they test for, then you can answer questions that say, how am I going to figure out what's what? What other type of questions do you guys have? Well, shit, let's just do the test tomorrow then, obviously. Go ahead.
This is on the they gave us a break over the reaction area. They said the dry HCl gave us.
So one of the things you'll notice I do on the homeworks is I draw reactions and I leave off the reactants, right? So this is really supposed to be saying, how well do you know your reactions? Meaning, you're mostly studying them, what reactants give you a product, right? But sometimes if you're given a product, you're given the reactants and you have to find the product, right? So what this is saying is, okay, so tell me what's those possibilities. So you have to start being a sleuth to a certain extent. What does the arrow tell you the reaction is going to be? Meaning, have you memorized that one? Yeah, see, like for instance, if you can say that this is a, not hemi, this is an acetal, right? If you can identify that molecule, then you should know what reacts together to give acetals, right? If you can look at the reaction arrow and go, we said that that's really a getting rid of water one, then we can do that, right? And so what you're really looking for is two things when added together giving you an acetal. Well, if you've remembered that a hemiacetal plus an alcohol are what gives you an acetal, that'll help. If you can remember that you're removing H2O, then what you're really doing when you get to this side, meaning going this direction, it's minus H2O, right? But what's it going this direction? Must be plus H2O. So if I break that apart and go something like that, there's my plus H2O, right? And then I can realize that if I have this molecule with an OH plus just methanol with an OH, then, you know, when I remove the water, that'll give me the right product. Some of it's a little bit of trial and error, but some of it's just being able to look up and recognize all those parts. My firm belief is also that if you can do something backwards, then you'll be better at doing it forwards also. Yeah, that's just one carbon. That's why I put the dots there, because the computer just draws a single line, right? And unless there's a bend in it, that means there's just a single carbon there. Or if we're doing it this direction, what we're really saying, remember, is that I'm taking this, and that then these parts are connected together, and of course the water makes water. So what's the opposite of a dehydration? Adding water to something. We're going to learn in this next chapter that's called a hydrolysis. One of the most important reactions in your body. Basically, half of the reactions when we get to talking about them in your body are either going to be dehydrations or hydrolysis reactions, meaning we're always adding water to something or removing water from something in our body. Because water is pretty easy to find, right? Yeah. Yep, that's just a single carbon. Like I said, draw the dots in there and ask me, and or, you know, yeah, actually that's probably the best way. Draw the dots and come up and ask. I don't know, what other types of questions are burning holes in your brains? So, for the test, realize that there's three parts, right? There's naming and drawing, and usually the drawing is easier for people. There's reactions, and there's the miscellaneous. So break up your studying so that you're doing one thing at a time. So my general recommendation is, and it's up to you guys what order you want to do it, but you know, if reactions are going to give you the most trouble, master them first and then just be able to practice those a little bit each night. Or if you think that, wow, if I just brush up on my naming and practice it real good, then I won't even need to study it the next 2 nights other than maybe just do one quick review. Or same thing with the miscellaneous. If I can write down all my intermolecular forces, I can draw an example of all my intermolecular forces, I can talk about boiling points and solubilities in terms of intermolecular forces. Once you've mastered that, it doesn't change. It's the same information, and it's even the same information for the next chapter. The only thing that changes is the functional group. And so if you can master one of those, then you don't have to worry about it, and you can focus on the other things. But pick one thing a night to master. If you try to master all that the day before the test, tough. If you've already mastered naming over the weekend, man, you're already a third of the way there. How many people mastered naming? And how do you tell if you mastered naming? Aaron? Yeah, print off one of those practice sheets, grade yourself. If you got 19 out of 20 or 20 out of 20, you've mastered naming. If you get 15 out of 20, well, think about it. That's on the test, 10 points off. You're already to a B. Oh, gosh, dang it. Hey, at least it didn't actually shut down, taking me every 15 minutes like the ex-wife. If you want to turn them in tomorrow, that's fine. Otherwise, I'll be here and turn them in during Todd's class this afternoon. I'll get them graded and handed out. That way you have them for the review tomorrow. Or turn them in tomorrow. It's fine.
Well, I just want to, now that I, read the numbers and stuff, I want to go try to
Where did my little tapey thing go? There it is.